Good afternoon, Buntun, Naren, Lee Hong, and Mr. C or Miss C, Remy, Rebecca, Ridareya. But I hope you are having a good day. And right after class, joining online class, it may not be hard. I mean, it may not be easy, right? But actually, if you make your coffee and I don't know, lying down and sitting and make yourself comfortable. I also made my coffee, and we are going to have only one session today, okay? And I'm not going to stop even after 40 minutes. I'm going to finish a few things. After that, we will finish class. Let's see how much actually we can go until I get tired. We are going to have this class, okay? So as you know, let's say we started chapter 5. It's about integrals, right? Actually, it's about definite integrals. And also we did a few, what is it? We made some introduction, and also we actually see that we have seen that how to find the area of a circle. That means that we need to use the idea of limit to get the exact area and blah blah. All right, yesterday we were talking about sigma notation, and you need to know a few sums to do a few calculations. One of them is the squares of, what is it, the sums of, how to say, the sum of the squares of the first n natural numbers. And thus I'm going to use this in this formula now. That's why we need to get clearer idea. Yes, so somehow we stop here. Let's just try to prove this one more time, okay? And after that, immediately I will use this to get some formula. So here to prove this formula, again, I'm just going to use this idea. So before the previous one, we have already proved that the sum of, what is it, the n natural numbers is equal to n times n plus 1 over 2. And now how about the sum of the squares of the first n natural numbers? So we are talking about here, it is s. Here. Okay. S is equal to 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared. That's equal to, just use a sigma notation as the here compact form, we can do that. So to do this one again, I'm just going to use this formula. We know that, for example, let's say if we just expand this one, here we have n plus 1 cubed minus n cubed, right? What is it? It is equal to, here we have n plus 1 minus n, and here we have n plus 1 squared plus n times n plus 1 plus n squared, okay? And the first part, n plus 1 minus 1, and n plus 1 minus n, that's equal to 1. And if you just simplify the other part, here we have n squared. I have also n squared here. I have n squared here. That's equal to 3n squared. Now from here we have 2n. Now I have here 1 times n. So here I have 3n, right? And what is left here? Here we have 1. That's it. So here we have 1. Okay, so n plus 1 cubed minus n cubed, that's equal to 3n squared plus 3n plus 1. Okay, so using this idea, instead of n plus 1, for example, if we have 1 here, what do we have here? Then 2 cubed minus 1 cubed, that's equal to, here our n is 1. So that's equal to 3 times 1 squared plus 3 times 1 plus 1. And how about if we have 3 cubed minus 2 cubed here? So that is our n here is 2. That is 3 times 2 squared plus 3 times 2 plus 1, right? One more, 4 cubed minus 3 cubed. That's equal to 3 times 3 squared plus 3 times 3 plus 1. Now, if you just continue this until n, for example, the last one is, let's say, n plus 1 cubed minus n cubed. That's actually the first formula. On the right hand side, I have here 3 times n squared plus 3 times n plus 1. Okay, so now if I just add all the left hand sides and right hand sides, right? See here on the right hand side, what we have here. If you just add the left hand sides, here we have 2 cubed minus 2 cubed. They cancel out each other. 3 cubed minus 3 cubed, right? And 4 cubed minus 4 cubed. And the last one here is something, right, or something, right? What is that here? Here we have only the first, this 1 cube, and the last n plus 1 cube. So on the left hand side, I have here n plus 1 cube minus 1 cube is just 1. On the right hand side, if you just look at this 3, 3, 3, 3, that is 3, right? Inside the parentheses, 3 is a common factor. I have here 1 squared plus 2 squared plus dot dot plus n squared. Plus, how about here? Also 3, 3, 3 is a common factor. Take this 3 out. So here we have 1 plus 2 plus dot dot plus n. Plus how many terms starting from 1 until n? So 1 plus 1, that's equal to n. Okay, so now what is our S? Capital S is what we are looking for. That is the sum of the squares of the first n natural numbers, right? So that means that let me just denote this sum by S. So I'm looking for this, okay? So now what we have here then? So let me just write one more time, this n plus 1 cubed minus 1. So that is equal to n cubed plus 3n squared plus 3n plus 1 minus 1, that's equal to 0. Here I have 3 times s plus 3 times, how about the sum of the first and natural numbers? In the previous slide, we have already done this. That's n times n plus 1 over 2. And still I have here n. Okay, so I need to find s here. All right, so to find s, let me just take everything to the left hand side. So here then I have 3s is equal to n cubed plus, if we have 3n squared, right? 3n squared, and this 3n minus n, that's equal to 2n plus 3 times this one, let's say n squared plus 3n over 2. So now let me just simplify this further. If you multiply both sides by 2, so I have here 6s, so I have here 2n cubed plus this one is 6n squared, and by 2 it is 4n, and here we have 3n squared plus 3n, right? So number one, actually n is a common factor. I can take this out, right? N is a common factor. 3n, 2n cubed, I don't have any n cubed here, so here we have 2n squared and 6n squared. So here 6n squared plus 3n squared, that's equal to 9n squared. So here we have plus, what is it? 9n, right? And here we have 4 plus 3, that's equal to, okay, that's 2. It is 6. This one is 4. Okay, we multiply both sides by 2. So it is 2n cubed, 6n squared. Okay, plus 1 minus 1. All right.
So is that supposed to be minus?
If you multiply both. Okay, 2n cubed plus 6n squared plus 2n. It is 4n. Okay, now here we have 6s. So here we have 3n squared plus 3n. Okay, n is out. 2n squared plus 6 plus 3. Okay, all right. It should be minus here, right? It should be minus here. Okay. All right. So this one n cubed plus 3n squared plus 2n. We just take to the left hand side, right? And also this one we are taking to the left hand side. It will be minus here. So now if you multiply by 2, then here we have 6s equals 2n cubed plus 6n squared plus 4n. Now here we have minus 3n squared minus 3n. And if you simplify this, n is a common factor. 2n, 6n squared minus 3n squared, that's equal to 3n. So plus here we have 3n. And 4n minus 3n, it is just n. N is out, so here we have 1, which is equal to, if we simplify this, and that is 2n squared, that's just quarter the expression. We can simplify this 2n times n, 1 times 1, their cross product is 3n. So that is equal to n times n plus 1 times 2n plus 1. Now if you divide both sides by 6, and we will get s. Okay, anyway, that is the proof of this one. Okay, and also this is so beautiful proof. And another one, we just take this as a fact. For this, you can use mathematical induction to prove this sum. I'll just take it now as a fact. Okay, we are going to use this. And also we talk about Riemann sum, and we are going to use this to solve some questions. And I really want to show this because now you need to have some kind of feeling that or understanding that just using this idea or definition to calculate this area, it is very, very tedious job. It is long and involves a lot of calculation. That's why actually this pushes the mathematicians or scientists actually to develop this method. That's why actually we need to develop this method, and we will get into this with the fundamental theorem of calculus, which actually makes our calculation very fast. Okay, so that is from exercise 5.2, and I'm going to show you one example here, some other examples you can practice with your TAs. In this question, it says that for the functions in exercise 43 to 50, find a formula for the Riemann sum that we just talked about the Riemann sum yesterday, obtained by dividing the interval AB into n equal subintervals and using the right-hand endpoint for ECK. Then take a limit of these sums as n approaches positive infinity to calculate the area under the curve over AB. Okay, so as you see here, they involve just constant number, right? 1 or x is a 2x or x squared or x cubed. If it is higher than this, what happens? X to the power 4, for example, is also okay, but it involves more and more calculation. Even, for example, just these things, let's just do the last question with you here today, 50. And also it involves a lot of calculation, a lot of limits. But for example, before I continue, suppose if you remember from high school, here it says that the area, right, over this interval. Suppose that it is actually here, we are talking about this graph. Let's say this one is y and this one is x, right? And here we have -1. Its value at -1, it is 1, 1, that's equal to 2. So this point is, it is 2, okay? Let's say it is area something like this, okay? So we are talking about this area. So under this curve, right, we are talking about this area. All right, we are talking about this area. How do you find this area? To find this area simply, we just need to calculate this integral, right? That is from -1 to 0. And here we have x squared minus x cubed. Here we have dx, that's equal to x cubed over 3, the first one, minus x to the power of 4 over 4, the second one. And here we have integration limits from -1 to 0. So when it is 0, both of them are 0 because they involve x, so it is 0 minus, one is -1, the first one is -1 over 3, minus the second one is 1 over 4. Because of this minus, it is plus, so that's equal to 4 plus 3, that's equal to 7 over 12. And units squared, that is the area, right? So using integral, as I say here, it's just a one step. Okay, but what are we doing here? We are using the fundamental theorem of calculus, part 2, actually here. Okay, and that's why it is so easy. Now we are going to read this conclusion after calculating this area without using this formula. And until people discover the theorem, okay, and they actually use just the definition and these methods that I'm going to show you here. All right, so let's do the last question. Again, it says that find a formula for the Riemann sum obtained by dividing the interval AB into n equal subintervals and using the right-hand endpoint for ECK, then take a limit of these sums as n approaches positive infinity to calculate the area under the curve. All right, our function is x squared minus x cubed over the interval -1 to 0. So that's our equation. It's 50. Our function is, what is it? It is x squared minus x cubed, right? So as you see here in the graph, we are talking about this region. I have already put here using Graphmaticum. So we are talking about this region. We are going to find this interval. So that is our interval is, what is it? From -1 to 0. -1 to 0. So now I am going to divide this into n subintervals. So that means that here, by using Riemann sum, right? So how can I form Riemann sum? Let's say x sub 0 is equal to -1, right? And by just adding this one is x1 and x2 and x3 and x4, blah, blah, blah. And the last one is xm. So our last point is, it is x sub m, right? So that means that let's say they are equal space, right? And what will be the length of one interval, right? So let's say that is delta xk, right? What is delta xk? Delta xk is equal to xk minus xk minus 1. But here I am dividing this into n subintervals. So actually it will be, what is it? B minus a over n. And what is b? It is right endpoint, that's 0. A is minus 1. So that is 0 minus minus 1 over n, which is equal to 1 over n. Okay, that is our delta xk. Okay, now from here it says that using the right endpoint, right? So the right endpoint means here I need to take, for example, x1 and x2 and x3, right? So that means that here I'm going to what is it? Form the Riemann sum. So our Riemann sum is here. It will be okay. This will be our Riemann sum, right? Let's say this Sn. That's our Riemann sum, and that is from k equals 0 to n, right? And now I'm just going to take this one, f of c, right hand side. So that's equal to, let's say, k, okay, times delta x sub k. Okay. So now, what is our function? This f of ck this is our function, right? Instead of x, I need to substitute c sub k. So what is c sub k? As you see here, for example, c sub k is equal to k times 1 over n. Simply, that's equal to k over n, right? For example, here, the c sub 0, it is negative 1. C1, right? It is just multiply this by 1. So we are talking about this point, right? What is this point? This point is 1 over n, and k is actually it's x sub 0. Okay, let me just write here, for example, if you just write, draw this line segment here, c sub 0, starting from here, this one is c sub 0. That's equal to negative 1, right? And what is C1? C1, it is negative 1, right? It's negative 1 plus 1 over n, right? And how about the second one? This one is C2, for example, C2, that is negative 1 plus 2 times n. Because each jump, right, is equal to 1 over n. The length of the jump is 1 over n. Okay, and the last one will be minus 1 plus n times 1 over n, that's equal to 0. So this one is c sub n, that's equal to 0. Okay, so now from here we'll see sub k then. So then c sub k is right, starting from c sub 0, right? That is c sub 0 plus k times 1 over n, which is equal to, what is t sub 0? It is negative 1. That's equal to negative 1 plus k over n. Okay. So that's our c sub k. Or simply, I can just write it as k over n minus 1. If k equals 1, for example, it gives us the first point. If n equals 2, for example, it gives us the second point, right? Actually, taking in the question, it says that dividing the interval a b into n equal subintervals and using the right hand endpoint for e sub k, right? So I need to use this one, actually, this c sub k. So instead of this one, then I need to write, what is it, k change not from 0 to n. So c n k change just from 1 to n. Okay. 1 is equal to n. 1 is equal to n, c sub n, that's equal to, it is minus 1 plus n times 1 over n. Okay, that's correct. Right, for example, let me just write, for example, f of cn. What is it? It is c sub 0 plus k is equal to n times 1 over n. C sub 0 equals negative 1, n is equal to 1, that's equal to 0. Okay. Anyway, that's how we are forming this. Now, let me just find first this. What is this? This f of c sub k, f of c sub k times delta x sub k. right? Delta x sub k, we know that that's equal to 1 over n. That's equal to 1 over n. And f of ck is equal to, what is it? Over n minus 1. So if you substitute into our function, then that's equal to, here we have c sub k squared minus c sub k cubed. And here I have 1 over n. What is c sub k? C sub k is k over n minus 1 squared minus k over n minus 1 cubed. And outside here I have, what is it? 1 over n. So now we need to find the sum. So that's equal to, all right, that's equal to, if you simplify this, let's simplify this quickly. If you simplify the first part here, we have k squared over n squared minus 2 times k over n plus 1. The next one is minus k cubed over n cubed. It is minus, so with this minus, it is plus 3 times k squared over n squared. And the minus, it is plus again. With this plus, it is minus 3 times k over n. And it is plus, it is 1. And the side here we have 1 over n. Here we have 1 over n. Okay. So I can just simplify this as see here k over n squared here. K over n squared is here, and k over n squared is here. We have 4, and k over n is here. We have 3 more k over n. We have 5, right? So, and it's just right here. I will continue. That one here equals. Okay, and let me not use red. I want to use blue here. Okay, first, what I have here is k cubed over n cubed, right? So first I have here minus k cubed over n cubed. And next one is, okay, this is gone, right? Now k squared. So here we have 4, right? That's equal to plus 4 times k squared over n squared. And after the k over n, here we have negative 2 and negative 3. So here we have 5 minus 5 times k over n. And okay, k over n also done. This is 1 plus 1. Actually, it is minus, right? It is minus plus, actually, minus plus minus. With this minus, it is plus. Okay, so here we have 2. So here we have 2 plus 2. And outside here we have 1 over n times 1 over n. Okay. Anyway, so now we need to find this sum, right? The k is changing, right? So if you just bring inside this 1 over n inside, so I will have here then, I will have here, this one will be 4, right? And this one will be 3, and this one will be 2, and this one will be 2 over n. 2 over n. Okay, so that's it. Now, if you remember at the beginning, what we have on the left-hand side, I have on the left-hand side this, okay? So now I'm going to form my Riemann sum then. Now, what's our Riemann sum? That S sub n is equal to sigma, right? K is changing from 1 to n. Here we have f of c sub k times delta x sub k. So that's equal to, now I'm going to substitute here. As you see here, I'm just going to write them separately. Okay, the whole thing is equal to the above expression. Okay, now that's equal to, if you write the first one, as you see here, n is not dependent on k, right? So that's equal to minus 1 over n to the power of 4. Here I have sigma, and the k equals 1 to n. So I have here, what is it? K cubed, right? And the plus, the second one is 4 over n cubed sigma. I have here k equals 1 to
2.
n. Here we have k
Okay.
squared. Minus, next one is 5 over n squared sigma. K equals 1 to n. Here we have k. And the
Okay.
plus sigma 2 over n. Okay. So now we know how to find the sigmas, right? The first one is, let me just simplify again, minus 1 over n to the power of 4. What is it? It is just the sum of the cubes of the first n natural numbers. And what is it? That's just equal to n times n plus 1 over 2 squared. So that's equal to n times n plus 1 over 2 squared. And next one is plus, I have here 4 over n cubed. And the sum of the, what is it? Squares of the first n natural numbers. And also that's equal to, what is it? That's equal to n times n plus 1 times 2n plus 1 over 2. Next one is minus 5 over n squared. The sum of the first n natural numbers, that's just k, that's equal to n times n plus 1 over 2. Plus, and just here we have 2 over n outside, right? The sum of ones, right, until n. So that's just equal to n. Now let me just simplify
Professor,
this, and after that we will find
uh,
its limit.
sigma k square
It's just the
n
approximation of
over
the area.
6.
How do I know the area? Because those rectangles, they're all positive. Our function is positive over the given interval from minus 1 to 0. That's why it gives us the area. Anyway, this simple algebra here, we have n squared, the first one, right? N squared, they cancel each other. And the 2 squared is equal to 4. So I have here minus 1 over 4 times inside I have n plus 1, right? Because n squared is gone, n plus 1 squared, n squared. So that's here I have here n plus 1 over n squared. Plus, next one is this n, they cancel each other. I have two n's left, so I can write it as, what is it, 4 over 2, that's equal to 2, times, bring this in inside, I can just write it as n plus 1 over n, times, actually guys, this n plus 1 over n, I can just write it as 1 plus 1 over n. The next one is, what is it, 2 plus 1 over n. Minus, here we have 5 over 2, 1 and they cancel each other, n plus 1 over n, that's equal to 1 plus 1 over n, and my plus 2. K2, the whole over 6. Yes, thank you, Seha. Let me see. Thank you very much. This should be 6. Oops. It should be 6. So 4 over 6, it should be 2 over 3. Seha, thank you very much. So now we are just assuming that again, the idea is like, if you remember the circle, if you just improve, right? I want to improve this approximation. How? I will increase the number of these rectangles. That means that n should be bigger and bigger. So this n, if n goes to positive infinity, actually it gives us the exact area. Then area under that's, let me change the color here. That's another step. So the area, right, that's equal to then the limit as n goes to positive infinity, this Sn. It gives us the exact area. And what is our Sn? This is our Sn, right? That is our Sn. So I need to calculate this limit as n goes to positive infinity. Now, if you look at the first interval, let me just write here, as we know that this n plus, not n plus 1 over n, that's equal to 1 plus 1 over n. It approaches 1 as n goes to positive infinite, right? So looking at the first
Professor.
one actually is equal to just 1, so that's equal to minus 1 over 4. Plus the second one, actually 1 over n, it goes to 1, right? 2 plus 1n, so here I have 2 over 3 times 2. Minus the third one, it is 5 over 2, and plus it's just constant. All right, there's a message. Here's Liu Hong. Where?
Sir, actually, a mistake there is supposed to be 1 plus
Liu
1
Hong, just a
over
minute,
n.
just a minute. I can hear you
The
well. Just a minute. Let me.
uh, so can you hear me now?
Yes, now I can hear you. Yes, I can hear you, Liu Hong.
Okay, so the mistake was 2 over 3, 1 plus 1 over n square, not n.
I don't get it. Can you say again? Are you talking about this? This one?
Uh, uh, no, no, the bottom one, like 2/3.
This one?
Yes, it's
Okay.
supposed to be 1 plus 1/m square.
No, why? Here we have this n, right? Actually, let me just write here. Here we have 4 over n times n squared. Here we have n
Okay,
times,
okay. I
okay?
I see I see my mistake. Okay,
Okay, good,
it's okay.
thank you. Thank you. So guys, let's continue then. So actually, I'm just calculating its limit. Okay, again, as you see here, that's the 1 over n. It's just we are using this IE. Now, if you simplify this, what we have here? Here we have, okay, let me simplify this. Here we have minus 1 over 4. And here we have 4 over 3 minus, and this one is 2. 2 times 2 is 4 minus 5 plus 4, that's equal to 1. And common denominator here is, what is it? It is 12. The first one minus 3. The second one 4. 4 times 4, it is 16. And minus, what is it? It is 6, which is equal to 3, minus 9, right? It is 7, sorry. It's minus 9 plus 16, that's equal to 7 over 12. Okay. And also using the integral, if you remember what we got here, we got 7 over 12 in just one step. But using the definition, as you see, it's very, very long step. And that's why actually mathematicians, they actually kept thinking about this every time calculating this one. These are just simple polynomial function. And how about sine function, trigonometric function, or higher degree polynomial function? It will be not complicated, but it is very long. Okay, that's why now this pushes us to develop this method, and we are going to give, what is it, the first fundamental theorem of calculus. Okay, anyway guys, that's all about this. Okay, I'm just closing this. Now let's move to our next session. Okay guys, 15 more minutes. Okay, after that I'll finish the class, but okay, 5.2. Okay. I will just stop the class after 15 minutes, okay? Because I don't want to give a break. If we give break, we'll lose a lot of time. So 15 minutes. Let me just hit my timer. So that's okay. 15 more minutes. So guys, now as you see, you got some idea. Actually, area estimated with finite sums. This is first it started. Okay, the sigma notation, limits of finite sums. It's not like, okay, they just did this for a few days and discovered this method. No, it took years actually, even until actually this mathematicians found out that fundamental theorem of calculus. They proved the theorem. They had been using that method, using the definition and very long methods. And as I told you, even in the history books, they say that actually after they discovered this rule, that the rule, what is the rule here? The rule is the relationship between the differentiation and integral. Right? Last time when we talked about indefinite integral, as see here, if you differentiate the integral, it gives us the original function, right? If you just integrate the function, it gives us, anyway, so if you integrate the function, it gives us antiderivative of the function. So now here we'll talk about the definite integral. So to that limit, that Riemann sum, right, when n goes to positive infinity, right, we need to give a special name actually. That sum, if that limit exists, we are going to call it a definite integral of f of x, or at the function f over the given interval. So let f of x be a function defined on a closed interval a, b. We say that a number j is a definite integral of f over a, b. Again, that j is the limit of the Riemann sum. Let's see here, first we are forming the Riemann sum, and calculating this limit. Does it exist or not? If it exists, okay, then we are calling this a definite integral of f over that integral. If the following condition is satisfied, the condition is just the definition of a limit that you study in chapter 2. So let's say that given any number epsilon, positive epsilon, there is a corresponding number delta, such that for every partition of AB, where actually this the biggest partition, this one is the norm. Norm is actually you're just dividing our interval into smaller subintervals, and I'm just picking the interval which has the longest length. And even the longest one is less than the delta. That means that all our other subintervals are smaller or shorter than delta. And any choice of ck in that interval, x sub k minus 1 and x sub k, we have this just a definition of that limits. Or simply, actually, if this Riemann sum when n goes to positive infinity, if this sum actually, if this limit exists, then we are just defining this as a definite integral. So is a symbol actually that we are using again this integral symbol from a to b f of x dx. X is the variable of integration. So now immediately the question comes then, okay, all right, we know the definition now, but every time we are just using the definition and checking the limit exists or not is also a tedious job. Now the theorem actually makes our ways shorter. So if a function f is continuous over the interval ab, or if f has at most finitely many discontinuities there, then the definite integral exists and f is integrable over ab. Okay, so that means that now if we are given a continuous function, without any question, it is integrable. We can integrate this, or without any doubt, we can integrate this even if we have some discontinuity over this AB, but it is countable, okay, maybe a few, not infinitely many. And that are even those functions because we can divide them into smaller parts and that we can integrate this. Okay, it's just one example for to show that this kind of function is not integrable because here it says that f of x is equal to 1 if x is rational. If is equal to 0 if x is irrational. And is it integrable over the interval AB? I mean 0, 1? It is not. Why? Because if you just pick any two numbers here, between any two number, we have rational number, also irrational number. Okay, it's a lot, too many jumps between any 2 points. That's why it's a real function. It's not integrable. Anyway, here we have properties of definite integrals. These are just simple properties. Again, using this definition, we can obtain all of these properties. Maybe next time, if we have more time, we are going to prove them. Okay. So when f and g are integrable over the interval ab, the definite integral satisfies the following rules. Number one, from a to b, right? From a to b, the integral from a to b f of x dx is the same as minus from b to a. Why? Because now from a to b, we're not just taking this, a is smaller than b, right? So that means that our actually this length, it is plus. But if you just count this from right to left, at the time it will be minus. The only difference will be minus. 0 with interval. The interval from a to a at a single point, right? So at a single point, our delta x is equal to 0. That's why its integral is 0. Constant multiple, again, if you just like limits, if you just multiply a function by k, it's a constant number. After all, this integral means a limit, right? So we can just take this k out. So the integral does not change. And sum and difference, again, f plus g, integral, the sum of the integrals is equal to the sum of the integrals of those functions. Additivity, that is one important rule. The integral from a to b plus b to c, it is the same as from a to c. Right? If you're given, for example, a line segment, and this one is a, and this one is b, and this one is c. And again, just you can just integrate the function from a to c, or first a to b, and after that b to c, and add them up. It gives us the same results. And property 6, maximum minimum inequality. If f has a maximum value, let's say max f, and minimum value, minimum f on AB. And also we know that actually from chapter 3, right, if you're given a continuous function over a closed interval, then it must have a minimum value and it must have maximum value. Then it says that here minimum value of f times b minus a is always less than or equal to this integral. Actually, here, if f is positive, you know, it's just the area times maximum value of f times b minus a. Okay, and the dominance, we have also one more property. F is greater than g on AB, then also its integral over that interval must be greater than the integral of the function g. Anyway, guys, here we have some examples. That's the last example. I will stop here and we will talk about more next week. Okay, that is the last example. Suppose that we are given this integral, but still, guys, we don't know some other actually exactly how to calculate this integral, because until we discover, actually, we understand that first fundamental theorem of integral, actually, you need to have some kind of feeling that's actually even we have these properties, using properties and calculate a lot of integrals, it's very hard. And that's why after we actually study the theorem, we will do our calculations much faster. Anyway, just using the theorem, for example, properties, how to calculate this? The integral of f from -1 to 1 is equal to 7. Integral of f from 1 to 5 is equal to -3. From -1 to 1, g of x is equal to 11. Now from here, it is 5 to 1, f of x, right? As see here, from 1 to 5 is equal to -3. So that means that that's equal to minus integral from 1 to 5, f of x dx. And from the above, we know that's equal to -3 minus -3. So this integral is equal to 3, right? And next one, using the property from -1 to 1 is given, right? I can just write it as 3 times integral from -1 to 1. Here I have f of x dx minus the second one, 5 is constant. I can take this out from -1 to 1. Here we have g of x, and here we have dx, right? And -1 to 1 f of x dx, that's equal to 7, right? So here I have 3 times 7 minus 5. From -1 to 1 g of x dx, that's equal to 11. So here we have 11, which is equal to 21 minus 55, that's equal to minus 34. And the last one from -1 to 5, right? Again, using the additivity rule, I can just split this into 2, -1 to 1, f of x dx, plus from 1 to 5, f of x dx, which is equal to -1 to 1 f of x dx, that's equal to 7. From 1 to 5, f of x dx, that's equal to -3, which is equal to 4. Okay, guys, I'll stop here. Okay, from here we will continue next week. On Monday, you will have quiz from chapter, what is it? Maybe Monday, maybe Tuesday, I will see. All right, most probably Monday. When it's just actually, anyway, you should just expect a quiz next week from chapter 4. And you need to answer like 10 questions. Again, it will be online, and some questions may be multiple choice questions. Some questions may be short answer required question. You need to write your answer in the box. Thank you very much for your attentions and patience. Okay, have a nice weekend. See you next week.